So we're looking at our first sort of mathish types problems here. Shine this up here, turn the projector on. This worksheet has 3 problems on it. These are sort of the most basic kind of setup of problems where if we're making a problem more complicated or I guess more something, it's like adding an extra detail or adding something to your car that makes it more complicated. But the baseline is basically explained in these 3 problems here. I'm going to have you write some stuff on the top, which are the equations first. And they're up there, but they're hard to see. So we're going to write what our sum of our forces in the x direction is. So when we write our equation, this means that all the forces that are going to be pointing to the right are going to be added, which is why there's a plus in front of it, or it's positive. All the forces that are going to the left will each be subtracted. And that way of adding and subtracting will allow us to figure out the acceleration of whatever mass we have. So in the acceleration in the x direction. And to be clear, what is the actual equation? This is the equation where you're actually doing math. This part right here is just telling you that you are dealing in the x direction. Similarly, in the y direction, all the forces that are going up will be added. So up, plus, 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 plus. All the ones that are going down will be subtracted, like the force of gravity and others. And that sum of the forces up and down will equal your mass times the acceleration in the y direction. Like I said, this is the part of the equation. Other stuff we saw yesterday, we saw that the force of gravity, not gravity, but the force of gravity, also known as the weight, can be found by taking the mass times the acceleration of gravity. And we're using positive, not because we're saying it's up, but we're just saying that the magnitude of it is positive. We will decide that it's down by realizing the force of gravity is down and then indicate it there. And then the last thing with our equation we just figured out is the coefficient of friction, which tells us how rough a surface is. And we can find that based on the force of friction divided by the normal. My goal ultimately is to never make problems that are cookie cutter, meaning that, hey, we're only going to solve these specific problems. We sort of had that in projectile motion, but fourth equation, second equation, but it was just because we noticed that. I'm trying to show that no matter how complex our problems are, we're always going to start out with the same steps each time, not try to overthink it in the middle, see what we have to work with, and then do algebra from there. So let's read through the problem here. It says a 1,250 kilogram box is pushed with a force of 5,000 newtons, so it accelerates to the right with an acceleration of 0.2 meters per second squared on a surface that has friction. It's asking us for the friction and normal. Ultimately, we're trying to find what the coefficient of friction is, how rough is this surface. But notice we have to figure out the force of friction and the normal force first. So sometimes we'll be solving A, then B, then C, but other problems we may not go in that order. It's not something you have to memorize, you'll just see how the problem. We could write our stuff out to the side. I'm just going to make it a little bit easier by underlining and saying, okay, that's our mass, kilograms. The only SI unit that has a prefix, so no converting to grams. This is a force. Which force would this be? This is our generic force. It would be applied force, yep. It says that it accelerates at 0.2. We should get into the habit of figuring out, is that A of x or is that A of y? A of x means it's accelerating sideways. A of y means up and down. It says it's to the right, so it makes sense that that's 0.2. But why this is helpful is that will automatically mean that A of y is 0 here. Whenever we're dealing with a single object, we will try at the utmost to always make sure that one of these is 0, if not both of them. We'll get to scenarios later where you say, how in the world can we do that? And we'll manipulate the problem. Next thing it says to do is draw the free body diagram. How can we write the equations unless we draw the free body diagram? You don't have to put the surface there. I think sometimes it's helpful, especially just realizing what's actually going on. All of our forces will be drawn from the center outward, which may be different from engineering courses or others you had. And these are the forces that we had talked about before, whether we have. So kind of going through the checklist saying, is there gravity? Yes. And that's always down. Sometimes it helps just to show that, hey, remember F of G, reminding ourselves that that is not 9.81, it is M times G. Is there a surface? Yes, the surface is pushing perpendicular, which in this case is straight up here. Now I want to clarify something. Mathematically, it doesn't really matter how long you draw these arrows. Conceptually, I think it will help you, but you're never actually expressing how long the arrows are. So minimally, as long as you have the correct labels and they're going in the correct direction, that's great. We do have a force that's being applied, so it accelerates to the right, so it's applied to the right. And then force of friction always opposes the motion of travel. This thing is moving to the right, so the force of friction would be back to the left. So once we decide, okay, we don't have any air resistance, we're never going to have air resistance. I misstated that AP doesn't do air resistance. AP has about a 1 week section where they do air resistance. They're actually in it right now. But there's an equation based on density and all this other stuff they use to calculate that. There's no rope or cable, so that's all the forces we have. Still not trying to say, okay, how exactly are we going to solve for this problem here? Start out, write your equation in the x direction, because it's not always clear where are we going to go, how are we going to solve this. So our equation in the x direction is all of our forces pointing to the right will be positive. We just have one in this case. Please write the variable out blank before you plug things in. Not only is that a very helpful thing to do, but sometimes there might be problems where there are no numbers. Or you're taking an AP class where you have to write out the whole equation anyway. Subtract all the forces going to the left. It's always right minus left. It's not bigger minus smaller. It's always right minus left because we have determined that right is positive and up is positive. So F of A minus force of friction equals M times A of X. So this is our equation right here, and we'll have to decide, do we have enough information in here to solve for it? So let's now plug in what we know. It said that the applied force of here, the pushing force, was 5,000. We don't know the friction force, that's what we're trying to find. The mass of the box is 1,250. And we determined that the acceleration was A of X, so which is 0.2. No matter how well you think you are, or how good you think you are at algebra, always just take your time. I see weird things happen where people are moving variables. I'll show you mathematically how this is. I always like to have my answer in the end as the variable on the left equals the number on the right. But I'll show you how this actually, so force of friction would have to be added over there. So you'd have 5,000. I mean, I've had people divide things. I've had square roots come in here, and I'm like, what? So equals force of friction plus, what is it, 1250 times 0.2 is 250. And then that would be subtracted over the other side. So force of friction, 5,000 minus 250, or force of friction is 4,750 newtons. Now what I mean is that we had enough information, meaning we only had one thing we didn't know in one equation so we could solve that. That's not always going to be the case. When we get to the end of this problem, we'll see how that could be solved. Some of the forces in the y direction. I usually have enough space to do it up and down, but I wrote a little bit big. All the forces up minus all the forces down. So up, we have F of n. Okay, nothing else is up, so everything down will be subtracted. Equals M times A of Y. this thing is not accelerating up and down. If it's accelerating if it's moving sideways, it's not going to be accelerating up and down. So a of y, or this whole thing, is 0 on that side. F of n is not, or sorry, f of g is not g, it is mg, or f of n minus 1,250. The reason why we're using positive 9.81 is that we have already determined right there that it is going down. We don't want to doubly to say that it's going down. So that is the negative there. Move it over the other side, and 12,262.5 newtons. So that's that. And now we can find the coefficient. What I'm trying to show here, we have a few minutes left, is that, let's look at this equation even closer, this coefficient here. Almost every single scenario, the force of friction is going to be found in the x direction. Almost every scenario, the normal force is going to be found in the y direction. The x direction has nothing to do with the y. They are independent of each other, except when you're dealing with this coefficient. You now have some way to solve for this. There will be problems where we may not have enough information in the x. Let's say, hypothetically, what if we didn't know the force of friction? How could we solve for the force of friction if we knew what f of n was, or if we knew what this was, and we knew what the coefficient was? Once again, what if we didn't know this, but we knew normal force and we knew mu? Yeah. What I'm trying to show here is that there's basically three parts: this, this, and this. It's not always going to be solve for x, y, plug it in here. Sometimes we may not know enough in the x, but we can use the coefficient and what we know in the y to solve for that. Or vice versa. We may not know the normal force, but we can use the force of friction and that to find it. I'm trying to show you that that's how these problems that's how you can have different types of problems. It's not changing the essence of everything. It's just showing, you're still doing the free body diagrams. Now, what I didn't say is the coefficient here is unitless. You're taking force divided by force, and like I said, a ratio is almost, I think, isn't a ratio always unitless? Usually. If we divide this and we round out, we get 0.39, which is, I mean, I'm never going to have you memorize coefficient of frictions. That's just like a useless thing. But that would be about, if we said that rubber on dry concrete is 0.8, this is probably, I don't know, rubber on a slightly damp road. I don't know, like that. I'm trying to give you an idea. Yes?
How do you know what the unit is going to be for the force of friction and the
So it is a force, and all forces are always in newtons. Another thing, you can put this away. I want to ask this last question. You may see that the force of friction and normal force, why isn't the force of friction negative if it's going to the left? Because both of these are magnitudes. They're just telling you how big they are. If you want to know the direction is indicated up here in the actual diagram. So even though this is going to the left, and actually, if you solve a problem, let's start real quick. If you solve a problem and you get a force that is negative, that means that the direction that you said it was going is actually which way? In the opposite direction. We'll finish up the other ones on another day.